Okay, well, what's a fluid? Okay, the term is often referred to as a liquid. Okay, referring to things that are liquid, but it is also a gas. Effectively, anything that can flow can be a fluid. Okay, so we talk about things called like viscous drag and so on, and that's to do with fluids. So viscosity, the frictional forces acting between neighbouring layers of fluid when they're moving over each other at different speeds. Okay, so when objects move through fluids, you get viscous forces. Okay, effectively saying that, well, when you move objects through, like a boat through water, okay, then the water will be moving differently in different places, creating this viscous drag. Okay. Another one that is important is the drag component, essentially when you're going in freefall. Okay, when you first jump out of a plane, you've effectively got your largest acceleration. Okay, why? Because if you have a certain weight, that will be given by mass times gravity, and then your acceleration will then be equal to, in this case, your weight divided by your mass. Okay, your force over mass from F equals ma. And that will be 9.81 when there is no drag. Okay, ms to negative 2. Here's a vertical component. So in this case, okay, let's look at the values. If he's got an 80 kg mass, 80 times 10 for gravity will give you 800, and then 800 divided by 80 will give you an acceleration of 10. Or if you use 9.81, it'll be 9.81. Now down here he's got a drag component of 220, so that means he's got a weight force down of, let's say, 800, which through gravity is 10, just for easiness, and then a drag force of 220. So his resultant force will be 800 minus 220, and we divide that by his mass of 80, it gives us his acceleration, which is, I think, around about 7.25 meters per second. Whoops. Yeah. When he then goes faster again, he has 500, so it'll be 800 minus 500 over 80, and they'll be slower again. Okay. I think it's 3.75. So you see his acceleration is getting slower. He's not getting slower, but his acceleration is getting slower. So the rate he's speeding up is getting less. And then the last thing is when your drag effectively equals your weight, then you no longer have this thing here. You have like 800 minus 800, and divide that by 80, you get no acceleration. Okay, that's your terminal velocity. So let's look at sketching A, the free fall and absence of air resistance. Okay, effectively, if we're doing a velocity time graph, okay, velocity meters per second, and we graph it. Free fall in the absence of air resistance, okay, effectively you're going to accelerate constantly all the time. Nice straight line. Now we're going to do free fall with air present, okay. So what happens there is your acceleration effectively will start to decrease, okay, until you get to a point where you go to a flat line, which will be terminal velocity. And then free fall with air present and a parachute opening after terminal velocity is reached. So effectively you accelerate up and we reach terminal velocity. We're saying this person must be really wide for some reason. And then they open the parachute, they have a sudden deceleration because they're slowing down, and then they reach a new terminal velocity.